Hi class, today we're going to talk about our processor, Centria 49. My name is Maria Garcia.
I'm Vincent Cataraja, for the designers.
For our agenda today, we're going to talk about our origin, so how we came up with our name. We're going to talk about our processor, the MIPS processor. We're going to talk about the architecture overview, the baseline processor, our enhancements to it, a few verification methods. We're going to talk about a few future enhancements that we just couldn't get into this time. And we're going to have a little Q&A session.
Centria 49. So we came up with the name. It was actually a combination of our first names, but the second syllable. So Vincent and Maria, so Centria. And then 49 are our birth months, so April and September.
Yeah, we just thought it was a nice touch and it was a little unique, so we liked it.
Okay, so the MIPS processor overview. What is MIPS? It's a RISC processor, and it follows the Harvard architecture, which means it has two separate modules for the instruction and the data for memory. These are big Indian format, and they're byte addressable. So that's the Harvard architecture. We have see the instruction memory and the data memory. All right.
Okay, for the register set and data types, we have 32-bit registers. The first 15 registers are for normal operations such as add, subtracts. The next 15 registers are for special functions such as the stack pointer and the return address. We have two data types, signed integer first. Flags affected by it are the negative, overflow, carry, and zero flag. You can see the range right there, and the instructions typically used are an add, sub, and set less than, and set less than immediate. For our 32-bit unsigned integer, the flags affected are the overflow, which is set to the carry and the zero flag, and the negative flag is actually set to zero, so it doesn't matter here. You could also see the range here, and it's typically used in instructions such as add and sign and everything that's unsigned.
All right. Addressing mode.
Okay, for the addressing mode, we have first of all register, which is one of the most commonly used. It's utilized in register operations. We have an example here with an add. We have two source operands and destination register. It's also utilized for the jump register instruction, which is 32-bit address, which is stored into the source register in the register file. We have register indirect or register deferred, which is used for the load and store instructions. The offset is added to the source register for effective address calculation and then it's stored into RT.
Immediate is when we use the immediate value, 16-bit immediate, and sign extended. A pseudo-direct addressing would be like the jump or the jump and link, where we use the 26-bit jump address concatenated with the PC, four most significant bits. The PC relative is used in conditional branches, such as branch of equal, branch not equal, branch of greater than 0, or branch of less than equal to 0. And it updates the PC by adding the offset. Flags.
Okay, so for the flags, we first of all have the interrupt enable, which is pretty much used just for the set interrupt enable instruction. We have our carry flag, which is set if there's a carry on expression. Also when we borrow arithmetic. We have the overflow flag, which is triggered if there's an overflow for signed operations. For unsigned, we set it equal to the carry flag. We have a negative flag, which is triggered if the result is negative for signed operations. We have the zero flag, which is triggered if the expression is zero. This is for both signed and unsigned.
Instruction formats.
Okay, we have our R type. Our opcode determines what the instruction is going to do. For the R type, this is ignored and it's actually used by the function code. Our shift amount is just used for shifting. And we have our 5-bit source register, 5-bit target register, and 5-bit destination register.
iType is very similar, but we omit the RD and we omit the shift amount. Instead, we put in 16-bit immediate, and we use the opcode 31 to 26 of the register as the opcode.
Okay, for J-type, this 24-bit jump address is what's gonna update the PC for jump.
so here's the hardware view. That's the top level diagram. We have the CPU, which has the output ALU out is actually interfaced with the address bus for the data memory and the I/O unit. You can see here that the ALU out is 32 bits. However, for simulation purposes, we only connected to 12 bits of the address for data memory and the I/O unit. The D out is interfaced with the data bus for the data memory and the I/O unit. The outputs of I/O unit and the data memory are connected to the inputs DY and I/O for the CPU.
You added that I/O input to your CPU?
Yes.
Yes.
So this is something that we're gonna talk about. a little
Okay.
further later on.
So start with the IDP.
So we're gonna start off with our IDP.
Mm-hmm.
Okay. So we have a 32 by 32 register file. There were some modifications that we did up here. We're gonna get in touch with them a little bit later on when we talk about our enhancements. We have our ALU, which contains the 4 modules from our first lab, which was the ALU wrapper. The MIPS32, which contains the ALU logic. We have the multiply and the divide, which take care of multiplying and dividing. For multiplying and dividing, we have our notable registers. For multiply, the upper hold the results for multiplication and division. We have scratch registers that are updated every clock cycle. So RS, RT, LU, out, and PN. Couple of muscles. So we're gonna talk about some of that later on. Some of the additions.
Next, we're going to talk about the control unit. This is essentially the finite state machine that's responsible for outputting the control word that controls the IDP, the instruction unit, and modules outside of the CPU, such as the data memory and the I/O subsystem. Here, I highlighted this is the general finite state machine diagram for the baseline. We can see that the interrupt service routine is, this is actually a combination, collection of 6 states, but for general purpose, I just want to put it in one big circle. We see the fetch. The fetch is the state that's responsible for generating the instruction unit control word. The decode is for staging the operands. The arithmetic, mem access, and the branch are responsible for generating the function select outputs. And the write back states are responsible for generating the write enable and the destination addresses. And then these states are for updating the PC if the branch passes. See the arrow coming from the decode into the fetch? That's actually the jump and link. We were able to implement it in the decode, 2 states. This is the interrupt service routine, collection of 6 different states, where we see that the first interrupt state is when we store the return address, the PC into the return address, and pass the stack pointer into the RS register. Interrupt 2 will be, we pass that RS into the ALU out, and then interrupt 3 will be when we push into the stack, we pop into the DIN, the interrupt service address, and then interrupt 4 would be loading the PC with that address and updating the stack pointer by 4, adding it by 4, and loading the RT with the current PC. Interrupt 5 will be where we push the current PC into the stack and update the ALU out by 4 again, and stage the flags. And interrupt 6 is when we push the flags into the stack and assert the interrupt acknowledge and store the stack pointer into the register file. Here are the control words that are hot, or that are active in these states. Alright, so next is the instruction unit.
Okay, we're gonna talk about the instruction unit next. Right here in this PC select mux, we have our branch address. We have our jump address, our PCN for coming out of the IDP for return address and jump register. This new signal was added for our enhancement, which we're gonna talk about later on. This is then passed into the instruction memory for fetching, which is going to be outputted by the IR, and sign extended for immediate instructions.
I/O unit is very similar to the data memory module. with the addition of the interrupt request acknowledge logic. Yep, that's it. So we're gonna talk about the enhancements to the baseline.
So this is a baseline enhancement.
Mm-hmm.
We have input and output, which is essentially store warn and load word. For input, right after, we had to do a modification in the IDP, which was add access between the I/O memory and the data memory. So here in the state machine, after the staging the operands, we calculate the effective address, output it to DN, and then write it back into the register file. For the output, after staging the operands, we calculate the effective address and store it into the I/O memory.
Since, go back, can you go back slide?
Oh,
Backwards.
Now we go forward.
okay.
Is this related to DY and IO? Weren't those
Yes, they-
tri-state outputs?
So, DY,
Yeah, in other
Yeah.
words, the outputs from the IO and memory modules.
yeah, so DY is coming from the data memory, so right here we have a choice between choosing.
Yeah, but weren't they tri-state outputs? In other words, if they're tri-state outputs, they could be tied together on the same bus. You only need one bus. You don't need an extra 32 inputs to a processor. So that's 32 new pins on your processor. And so if you have tri-state outputs, you don't need that mux right there. So you try to limit the amount of pins to your processor if you can, and that's why you have tri-state buses. So wasn't it tri-statable? In other words, if the chip select for the memory wasn't used, the data out was in the high impedance mode. Similarly, if the chip select for the I/O module wasn't asserted, it would be high impedance. So they could be tied together on one bus, and you would only select one or the other.
Okay.
So that'd save you 32 pins plus that mux that has 64 inputs. All that costs a lot of money. Logically, no difference. No difference, but it's just something to think about on your next iteration process.
I'll work on it.
Okay.
These are the states with the control words that are active
Mhm.
For each state.
Next is the return from the interrupt. So this allows the processor to pop the pushed flags in the PC back into the PC and the control unit.
Good.
Alright, so we see after staging the operands eco state, we pass the stack pointer, the current stack pointer into the ALU out, and then use that as the address for the stack, and load, or pop the, what was the last one, push, flags. So pop the flags into the DN,
Mhm.
and then we return, we load it into the present state flags in the control unit, and
Mhm.
decrement the stack pointer by 4,
Right.
and then use that as the address for popping the stored PC into the DN, decrement the stack pointer by 4 again, and then update the PC with that return PC. And ALU out this time, just keep the same stack pointer, and then finally write the stack pointer back into the register file. Here is the sequence of states to accomplish the return from the interrupt, and the control word are highlighted. And this is the necessary modification to accomplish the return from the interrupt. So basically we added another mux that takes the ALU out as another operand
Mhm.
for the ALU operation, which is DEC4 or INC4. Push.
Okay, for push, so push allows the CPU to store word in the memory designated by the stack pointer, implementing it by 4. So here, after we stage the operands, we go into this push state, and this is gonna assign the stack pointer to the ALU. We're gonna go into the next state. We're gonna increment the ALU out by 4, so increment the stack pointer by 4, using the same path that Vince just mentioned. And we're gonna write back into, we're gonna push the data into the stack according to the stack pointer,
Mhm.
and then write the incremented stack pointer back into the register.
Mhm. Excellent.
And this is
The
necessary
modifications.
modifications.
So this is the one Vince talked about, and we're using this to push in the address.
Use the stack pointer as an operand into the RS.
Mhm.
And these are the states. signals are active.
Very good.
Okay, for the POP, it's a pre-decremented POP, which allows the CPU to load word from memory designated by the stack pointer decremented. So right after the staging the operands, we're gonna decrement the stack pointer using the function select decrement by 4. We're gonna do the same thing, go around through the ALU, and then go through the data memory and assign DN with that output, and then go through this state, in which we essentially feed the write back DN into the register file, and then store the stack pointer.
What's the opcode of 21? If you go back
Opcode
a slide.
21, oh, that's the IR 31 to 26. Can you go back? Right here.
We know MIPS doesn't have a POP instruction. They have reserved those 6 bits for their own instructions. Are you sure that the 21 wasn't used by any MIPS processor?
We didn't have a problem.
No, of course you
Oh.
didn't have a problem.
Oh, sorry.
But yours is now not a MIPS compatible processor. As soon as you start using opcodes that you feel are free to use, what gave you the right to use 21? And I didn't see what the push opcode was.
That's 20.
So in order to be compatible, we had a reserved opcode that they didn't use. 21, I think, is used by one of their instructions. Not by one you did, but by others. So you're no longer MIPS compatible. So the idea of the E key type thing, the 1E was, once it was 1E, then you could put the opcode somewhere else
Okay.
for push and pop and anything else. But you can't just steal opcodes. Easy change to make, but it's just a misunderstanding. Yeah, I can't let that one slide. That's huge. Because your processor should be able to run,
Their MIPS.
yeah, or not run into their 21, which is some other instruction. Yeah, I didn't notice on the push. I just noticed right there.
We'll work on that. And
They
it's
will
this-
work on it. they said.
So this is the same modifications as the push,
Mm-hmm.
and then these are the states that are where the control words are high.
Very good.
So NOAA, I guess, it's just an extra state after staging the operands where we set all the control words to 0. Yeah, that's it with opcode 27, but, and decrement branch not 0.
Okay, for decrement jump not 0, this allows the CPU to firstly decrement the register and check the present state 0 flag to perform a conditional branch until the decremented register contains a 0. So after staging the operands, we're going to decrement the source register. We're going to go into the state, check the present 0 flag, and if the flag is 0, then we're going to assign PC the branch address. And if it's not, then we're going to increment the PC by 4. And then we're going to write back to the register file.
Follows the I type. Oh, and the restriction.
The restriction for this is that RS and RT have to be equal. So yeah, that is something that we have to overcome.
Yeah.
In the
As far as the register code.
Yeah.
Yeah.
Here are the states for decrement branch not 0. See here, control words are highlighted. But then we had time to actually improve the decrement branch not 0, in which we omit the RT field and increase the jump address bit size. In this enhancement, we allow this, so it behaves as the decrement branch not 0, but the source address is also the destination address. So this eliminates the restrictions of the branch that we use RS and RT being the same.
So from a design team,
Yeah.
why would you even say that we have the other one?
Okay, so the thing was we first implemented the decrement
Yeah,
branch
yeah,
not
yeah,
0.
yeah.
But then when we improved the decrement branch not 0, we thought we just keep it since we can take it out though.
Yeah. This came out on Monday. You don't have things in there that, everything costs, real estate, power, complexity, you know. So if you don't need it, you just, because you found a better way, much better way, bigger range on the jumps, that's great. And nobody so far has had a DJNZ, and it's like, that's the best instruction you can have from a programmer standpoint.
Alright,
So very good.
Thank you. Alright, so here are the states that accomplish decrement jump not zero.
Mm-hmm.
So here, basically, the first state, we decrement, and then second state, we check the flags, and then we load the PC with the new jump address, where I will talk to you about the enhancement here, where we improve the destination address MUX. We passed in the S address as a destination. In the instruction unit, we also made the PC MUX bigger,
Mm-hmm.
so that we can implement the new decrement jump not zero
Mhm.
concatenation.
Mm-hmm.
Alright?
We have a jump carry and jump not carry, in which we check the carry flag, and then jump if it's asserted, or deasserted if it's jump not carry. We have it two states right here. This one's pretty simple, pretty straightforward. The same thing for the jump, if overflow or not overflow, but now instead of checking the carry flag, we're checking the present state overflow flag.
Mm-hmm.
Alright, so we also implemented the branch for the carry, branch not carry, as well as the branch overflow and branch not overflow.
And the difference is, again?
It's just less, actually the jump would be, we implemented the branch first and then implemented the jump, which was an improvement, bigger range. Decided to keep it, but we could scratch it. Right. Okay, so now we're gonna talk about the verification methods we use.
So one of the verification methods that we thought it was pretty essential to continue the project was like actually using breakpoints and then displaying results at the positive edge and the clock. So right here we see where we set the breakpoint. We see the results of AOU out, and then we open up the register file to make sure that it's actually in there.
Mm-hmm.
And this was actually pretty helpful for us.
Very helpful, right?
Yeah. So verifying enhancements, we had to create our own memory module. So here is a simple example of the push, the decrement jump not zero, the no-op, decrement branch not zero, and the pop. So basically, the first one, we initialize 13 with 3, keep pushing 3, register 13 until we decrement 13 to 0. And then we initialize 13 with 16, and then reiterate no-op 16 times until it's 0, and then finally pop the last push value into the register 27. And here are the results where, actually we used the data memory module 14, which initializes 3F8 with 0, but that wasn't used. Stack pointer started at 3FC, so initially 3, we pushed 3, and then 2, and then 1, and then when it was 0, it stopped, and it passed on to the add immediate 13. Now it has 16, and it's going to do no-op 16 times until it pops the last push value, which is 1, into register 27, and then decrement the stack pointer by 4. So it was at 408 before the last pop, and then now it's at 404.
Did you increase the size of your memory module?
No, I didn't.
How did you have addresses 400? Now the 400 is above 4K.
The 400 is, it's still 12.
Yeah, that's above 4K. Thought it was a 4K memory module. 3FF would be the last location of 4K. Anyway, something you have to look at.
Okay.
This is what Vince just said could just be seen here in this waveform. Right here, from here to here, is where actually the add instruction is going on. So we're just adding 3 to the register 13. We're starting pushing here, so this is where right here where we see this SP marks going on, that's where we go back and forth between the LU.
Mhm.
We're gonna keep doing this until the increment job not zero fails. So PC plus gets PC plus 4 here. So this is where it fails, this is where it becomes 1. He then added immediate 16 to R13 again, which is gonna go all the way to here. And then once the increment branch now fails, it's gonna push register 27 here. And then we see here what the LEU has to go around again for the pop, for the
Mhm.
last pop instruction.
These are the necessary modifications that you were trying to.
Oh, it's gonna go back and forth, but,
Okay.
and then,
Future enhancements.
okay, so for, originally what we wanted to do was floating point, but due to time constraints, we couldn't get to it, so this is something that, feel we could accomplish in the future.
Uh-huh.
Vince wanted to do a single instruction, multiple data also, so it was like conflicting of what we wanted to do too. So it's something that we're gonna implement in the future. And then pipelining, which of course it's what everybody wants to do, but it's gonna take some more time.
Q&A?
Any questions?
Boy, you'd think there's nobody back there, right? You know, it's an excellent job. My only comment would be, and it's an easy change. It's your decode unit. You can't have those opcodes. Those opcodes are all reserved. They're all used. So you're not running other code that uses actual MIPS instructions that used them, so yours worked. So that's all you'd have to switch to make it legitimately compatible.
I guess I misunderstood.
Yeah.
E.
Yeah. So then you'd have to just move the opcode somewhere else. It's kind of like an R-type. So once you see the 0, then you go down here. So you just move the opcode. So if it's a 1E, that's like 00. Now you go find it somewhere else.
Okay.
So it would only affect decoding, not your states at all. Just affects the decode unit. So that's a pretty easy switch to make.
Okay.
Yeah. But presentation was excellent. Very good job. Thank you.